Okay, so lesson 112, spend some more time with these shapes and just sort of dealing with the different attributes of shapes and these polygons and making sure that we're comfortable with them. So starts with a review of yesterday. So we get another Venn diagram, and now we have to break them up into a quadrilateral, which hopefully we know means four sides, and equilateral means all the sides are the same. So a square, well, it's definitely four sides and they're all the same, so I'll put that in the middle. A kite is definitely four sides, but they're not all the same, so I will just put that on the quadrilateral side. A rhombus, four sides, all the same length. A parallelogram, we have four sides, but they're not all the same length, so we'll go ahead and put that on the right side. A trapezoid is definitely four sides, but they are not all the same length. So just looking for the regular trapezoid. Having trouble finding. There we go. There's the regular trapezoid. So that's four sides, but they're not all the same length. A rectangle, four sides, but again, not all the same length. So a lot of quadrilaterals so far. A quadrilateral, clearly four sides, but not all the same length. An acute isosceles triangle. Well, there we go. An acute isosceles triangle is going to be neither. It's not four sides and they're not all the same length. Even though two sides are the same, they're not all the same. Equilateral triangle, they are all the same, even though it's not four sides, so it'll go on the right side. An isosceles trapezoid, it is four sides, but they are not all the exact same length. A scalene right triangle, all sides different sides, and it is not four sides. And a two scalene, I think I got the wrong one there. So first of all, I'm sorry, I wanted a scalene right triangle, that would go there, and now an obtuse scalene triangle, now that would go there. My apologies. Both end up in the same spot, but don't want to misname them. An isosceles right triangle, well, obviously they're not all the same. Two of the three are, but not all of them, and it's clearly not four sides. A hexagon, it is equilateral. They're all the same, but it is not a quadrilateral. A pentagon, they're all the same, but again, it is not a quadrilateral. And a right trapezoid is a quadrilateral, but they're not all the same. So that's how we would go ahead and break that Venn diagram up. So hopefully you recall that from lesson 111. Now, as we continue on in lesson 112, it says describing a polygon. So I'm going to go into another software package so I can write with this. Off on problem 111, so it says describing a polygon. How can you describe a square? With your class, find a way to describe a square using its attributes or special qualities so that anyone can draw a square based on your description. Be as complete as possible. You may not use the word square. Well, I would say the opposite sides. You know what? Let me do this. I would say opposite sides are parallel and congruent. Actually, let me change that. Not all sides are congruent. All sides are congruent. I would say that I have all four angles are right angles. It does occur to me that I probably should have stated at the beginning that it's a quadrilateral. Okay, so quadrilateral, four sides with the opposite sides that are parallel. That makes sense. All sides are congruent, and all four angles are right angles. I feel like that pretty much describes a square. All right, so it says each polygon in the bucket is unique. That is, it differs from the others. You will be assigned a few polygons to describe as completely as possible for the class. As you work with your team to create a complete description, consider the questions below. What do you notice about your polygon? What makes it different from the other polygons in the bucket? And if you wanted to describe your polygon to a friend on the telephone who could not see it, what would you need to include in the description? So we're going to get a polygon graphic organizer, which is going to look like this. It's going to look like this. In class, what would happen is I would give a couple groups, a couple different shapes, and then we would just sort of reconvene after that. So describe each polygon completely based on the descriptions you generated in problem 112. Note that a description for a rectangle is provided as an example in your graphic organizer. So let's go ahead and look at that rectangle. So it says it's a quadrilateral, so we know it's 4 sides with 4 right angles. We know it has 4 right angles. Opposite sides are parallel, so the opposite sides are parallel, and have the same length, so the opposite sides have the same length as well. Again, these carets, if you remember from integrated 1, mean parallel, and these ticks mean the same length. So sometimes kids have a tendency to look at these carets and think that means they're the same length. That's not true. It just means that this line is parallel to this line. These ticks go back and say that these lengths are the same side. And then it says it has reflection and rotation symmetry. So if we go back over here, kind of reading through, it says on the diagram for each polygon, mark sides that must have equal length or must be parallel, mark angles that must have equal measures, and mark angles that must equal 90 degrees. So read the instructions below. To show that 2 sides have the same length, use tick marks on the sides again. So those tick mark means the same length. It says use the same number of tick marks to mark every side with the same length. For example, AD and BC are the same length because they have 1 tick mark. If I go back over here, I know that these sides are the same length because they have 1 tick mark, and I know that these sides are the same length because they have 2 tick marks. I know that these lines are parallel because they have 1 caret, and I know that these lines are parallel because they have 2 carets. So that's important to remember. To show that the isosceles trapezoid has 1 pair of parallel sides, mark 1 caret mark for each of the parallel sides. To mark a second, use 2 like we just talked about. So here we would say that these are parallel. Mark angles with the same number of tick marks. So this has 1 tick mark and this has 1 tick mark, so we know these angles are the same. These have 2 tick marks, so we know that these angles are the same. It says mark any right angles with a corner. And then we're going to go through the polygon graphic organizer. So let me pause this and set this up. What I encourage my class to do is we need to get familiar with these tick marks. So I don't mind if you write it out in English, but I definitely don't require you to write it out in English. But I do require the tick marks. I think that they are very helpful for what it is that we're trying to do here. So I appear to have lost my pen. Let me find it. All right, sorry about that. So let's go ahead and mark up a couple of these shapes, and then we will go through and just look at the key of what it looks like. So if I had an equilateral triangle, what I'd say is, hey, look, I know that all of these lengths are supposed to be the same, so I'll give 1 tick for each, and I know all these angles are supposed to be the same, so I'll do that as well. What if it was an isosceles triangle? Well, I would know that these sides are the same length and these angles are the same. But this one would be different. I wouldn't actually have to mark that if I didn't want to. If you wanted to, you could use 2, but you could see how ugly it starts to get when you do that. So I would probably encourage you to just leave it like that. If I look at a scalene, that means everything is different. So if you wanted to, you could mark each one as a different length just so you discernibly know it was a scalene triangle. I would probably not mess with the angles, but a scalene right triangle, you're definitely going to want to put that right angle in there so everybody knows that you have a 90-degree angle. An isosceles right triangle, well, I know this is 90 degrees, I know these sides are the same, and I know these angles are the same, right? Square gets real messy real quickly because it's a lot like a rectangle. And at this point, I'll kind of show you what I mean as to why I am going to jump to the key here in a second as opposed to going through all this. But you can see what this begins to look like. So there we go. It just occurred to me that I did that wrong because a square has all of them the same. So that was dumb of me. So let me fix that. So I only need to have, oh jeez, I give up. Good night. Okay, I have 4 right angles. I hope nobody watches this video, because if you do, I probably should cancel. All the sides are the same length. Originally when I did this, I put different side lengths like a rectangle, but all the side lengths are the same. But when I do the parallel marks, you'll notice I do 1 for these and 2 for these because these are in fact different parallel lines. Bottom line is when you look at it, you can see it looks like a big mess, and that's where I think it's better off to jump over to the key here and just sort of go through these shapes. So you can see the equilateral is all the same, the isosceles, scalene right, like we talked about, isosceles right, the square, it looks a lot better here. Our rectangle, we'd already discussed. Parallelogram, we have opposite sides are parallel, and opposite sides are the same length, so it's like a squish square. And you'll notice the opposite angles are also the same, but not the same as each other. So we have 1 and 2 ticks as opposed to just 1 tick for everything. If I go to a trapezoid, we just have opposite sides parallel. A rhombus looks like a mess. All sides are the same length, opposite sides are parallel, opposite angles are the same. Quadrilateral, nothing special, all sides are different. A kite, 2 sets of same sides and the opposite sides are the same angle, but these are not the same angle, so that's important to remember about a kite. A rectangular pentagon, all sides the same length, all the angles are the same. Regular hexagon, all the angles are the same, all the sides are the same, but I would argue they probably should have a parallel line here and here, a parallel line here and here, and a parallel line here and here, right? We have those parallel lines that they didn't mark. Isosceles trapezoid. Isosceles is a little bit special. You'll notice that we have our parallel sides and we have the angles being the same, but they missed the marks. They should have put a mark here and they should have put a mark here, so they missed that on the isosceles trapezoid. And a right trapezoid, opposite sides are parallel, and we have our 90-degree angle. So hopefully you're okay with that. I know there's a lot going on with that sheet, but hopefully it gives you a chance to kind of look at it and to feel comfortable with it. Now, I'm going to go ahead and set up problems 14 and 15 real quickly. It says examine the Venn diagram below, and some of the polygons in the bucket have already been placed. So what attributes does each circle represent? Well, if I just look at circle 1, it certainly seems to be a triangle, right? That seems to be what that first condition is. The second condition, not as obvious, but it looks like we have to have at least 2 sides that are congruent, right? At least 2 sides. I can't say 2 sides congruent because this has 5 sides congruent. And again, we can tell because that's just what this looks to be, right? So where does the regular hexagon from your polygon fit? Well, it's not a triangle. So I think that, but all the side lengths are the same, so it has at least 2 sides. So I think it would go here. Our regular hexagon would go there. That looks like a fabulous regular hexagon, so I apologize for that. Just for our reasoning, again, it's not a triangle, so it can't go in one, but it does have at least 2 sides congruent. Now create another polygon that belongs outside of both circles. Name your polygon. What if I just said a regular quadrilateral, right? Nothing special, it's 4 sides, none of them are the same length, so a quadrilateral would be fine right here. I could also say like a just a regular trapezoid or even a right trapezoid would be fine there as well, right? So either it just couldn't be an isosceles trapezoid because an isosceles trapezoid would have to go there. And then finally, it's kind of tough to see. It says Elizabeth started the Venn diagram at right. It turns out that the only polygon in the polygon bucket that can go in the intersection where the 2 circles overlap is a square. So what possible attributes can our circles represent? Discuss the question. So again, just in case we're not going to look, we're just saying square is the only thing that could possibly be in the middle. So I would say one possible solution would be, what if we said that we have right angles, all right angles, but then it could also be a rectangle, right? So on this side, maybe we say equilateral. And remember, equilateral means all the sides are the same. So a rectangle couldn't be an equilateral. It has opposite side the same, but not all the sides the same. So I think that's one possible solution for 115. There may be others, but that's the one that popped into my head.